Working with 2D vectors. Okay, let's introduce this topic with a quick recap of some of the information we covered in the introduction to this section, as it helps set the scene for 2D vectors. Quantities can be scalars or vectors. Scalar quantities have size, which is also known as magnitude, but scalar quantities do not have direction. Vector quantities have both size and direction. So vector quantities have both size and direction. So let's take a look at a couple of examples. Speed is a scalar. We would say the car is traveling at 20 kilometers per hour. So speed has a size, but we don't know which direction the car is traveling, as speed is a scalar. The vector equivalent would be velocity. We would say the car is traveling 20 kilometers per hour north. So we have a size, 20 kilometers per hour, and we also have a direction. The car is traveling north. So velocity is a vector quantity. Okay, another example would be distance. We would say the school is 500 meters from the house, but we're not saying in which direction the school is from the house. We just have a size of 500 meters. The vector equivalent would be displacement. We would say the school is 500 meters due west of the house. We have both size, the 500 meters, and we have a direction, the movement west. So displacement is a vector quantity. Okay, that said, we represent vectors in diagrams using line segments. So let's have a look at the diagram on the bottom left here. We have points A and points B. Now, the line in blue shown with the lowercase a beside it is a vector. The vector A represents a movement from point A to point B. So this line segment represents a movement from point A to point B, and the line segment is the representation of vector A. So the direction of the vector is shown by the arrow, and as we can see, the arrow shows that we're moving towards the east, and then we're moving towards the north to move from point A to point B. Now we can work out the size of this movement, so we can see that we're moving 3 units to the right in this scenario, and then we're moving 4 units up the way. And the length of the line AB represents the vector's magnitude, and as we covered in the Pythagoras section of this course, you can see that we have a right angled triangle here, and we can use Pythagoras theorem to work out the length of line AB, so we can work out the size of the vector, and we will be covering that in more detail in a slide that is coming up in this topic. Okay, so this vector can be represented in the following ways. We can represent it with the lowercase a, as shown on the diagram. It's lowercase and normally highlighted in bold, and we say vector A. We can also represent vector A with an underline. This is normally used in handwriting, and we will also say vector A. We can also show vectors as directed line segments, which this directed line segment AB shows the movement from A to B. So the arrow represents the movement from A to B, and we would say this is vector AB. And the final way we can show this vector is in component form. So in component form, here we're showing that the vector A represents a movement of 3 units in the x direction to the right, and 4 units in the y direction up the way. So the vector A can also be represented in component form, and we'll talk to component form a little bit more in the coming slides. Okay, let's take a look at component form in more detail. So as we said, we can represent a vector in component form, and here we're showing in the top left a vector has components x and y. Now x and y are the components of the vector and tell us the size and direction of the movement. The x component tells us about the horizontal movement, and if it's a positive value, that represents a movement to the right, and if it's a negative value, it represents a movement to the left in the horizontal plane. The y component tells us about the vertical movement. So again, if it's positive, it'll represent a movement up the way, and if it's negative, it'll represent a movement down the way. So a vector in component form will tell us about the horizontal movement, how many units we move to the left or right, and the vertical movement, how many units we move up or down. And we'll see that in the diagram in a second. But one note here, this form is also known as column vector form. So we can say that this vector is in component form, or you might be told that the column vector of A is xy. Okay, So let's draw our first vector. We have vector p as shown. Now let's put this vector p into component form. Well, what does the movement represent? It represents a movement to the right of 3 units. So x is 3 units to the right, which is plus 3. And then it represents a movement up of 4 units. So y is 4 units up the way, so y is plus 4. Remember that movements to the right for the x direction are positive and movements up the way in the y direction are also positive. So we would say the vector p is 3, 4. We don't need to show the positive sign, it's inferred. So the vector p in component form is 3, 4, and we know that it's a movement of 3 in the horizontal direction and a movement of 4 in the vertical direction. Okay, let's have a look at our next vector, vector q as shown. So let's describe the movement from the start of the vector to the end of the vector. Well, we move 3 units to the left, so x is 3 to the left, and as we're moving to the left, this is negative 3. Recall that a horizontal movement to the left is a negative movement. And then we have a movement down the way, so y is 4 down, and again a vertical movement down the way is also negative. So this vector q would be represented by, in component form, as negative 3, negative 4. We're moving 3 units to the left in the x direction, we're moving 4 units down the way in the y direction. Okay, and our final vector here is vector r. Again, this is representative of 3 units to the right and 4 units up the way. So x is plus 3 and y is plus 4. So the vector r is equal to 3 over 4 in component form. 3 units to the right in the positive direction and 4 units up the way, again in the a positive direction. Now what we can see here from these two vectors is that vector p equals 3 over 4 and vector r also equals 3 over 4. So vector p is equal to vector r. Now this brings us to one of our vector rules, which states that for equal vectors they have the same size and same direction. So we say that vectors p and r are equal because they have the same size and they have the same direction. Now let's look at vector p again, components 3, 4, and vector q, components minus 3, minus 4. Now looking at this, we can notice that q is actually equal to negative p. And this brings us to another vector rule, and that this one is on opposite vectors, or also called negative vectors. So opposite vectors have the same size but opposite directions. Now looking at our diagram, you can see that vector p and vector q, if it weren't for the arrow, the line segment is actually the same. The only difference between p and q is the arrow, the direction of the movement. Vector p represents a movement 3 units to the right and 4 units up the way, and vector q represents a movement 3 units to the left and 4 units down the way. So p and q are opposite vectors. Let's take a look at how we multiply a 2D vector by a scalar. Now in the diagram on the left we can see 3 vectors, vector p shown in blue, vector r shown in orange, and vector s shown in green. On the right hand side we can see these vectors in component form. P is 2, negative 4, which represents a movement 2 units to the right and 4 units down. R is the vector 4, negative 8, which represents a movement 4 units to the right and 8 units down. And S is a smaller vector, a 1, negative 2, which is 1 unit to the right and 2 units down the way. Now we can see that P is twice the length of S. So P, the vector P, is 2, negative 4. And we can see that this is the same as 2 times 1 and 2 times negative 2. So taking the 2 out of the brackets, we could say that P is 2 times the vector 1, negative 2, and we know that 1, negative 2 is S. So in vector form we'd say that P is equal to 2S. So vector P is 2 times vector S, and 2 would be our scalar here, our multiplier. We could also rearrange this and say vector S is equal to a half of P. So we can represent one vector in terms of another where there is a multiplying factor or scalar involved. Now let's look at vector r. R is 4 times the length of S. So r is 4, negative 8, which is equal to 4 times the vector S, 1, negative 2. So r is equal to 4s, and again we could represent r in terms of p, and we could say r is equal to 2p. Now what we're showing here is that we can represent one vector in terms of another, and there's a general rule which we use for this. So the rule is b equals k times a, where k is a scalar quantity, our multiplier. A and b in this scenario are in the same direction, they are parallel, and you can see that in the diagram. P, R and S are all in the same direction, they're all parallel, and b is k times the length of vector A. So in the scenario where we have p equals 2s, obviously p is 2 times the length of vector S. P and S are in the same direction, but P would be 2 times the length of vector S. So this is our general rule, where B equals K times A and B are in the same direction, and B is K times the length of vector A. Now one additional note on multiplying by a scalar. Let's look at the additional note through an example. So we've drawn on the left hand side of the screen, we've drawn vector AB, which represents a movement from A to B. In component form, vector AB is 0, negative 4. We're not moving to the right at all, we're just moving 4 units down the way. Now let's draw on vector MN. Now you'll see that MN is 0, 2. And looking at this 0, negative 4 and 0, 2, we can see that AB is equal to negative 2 MN. So what this tells us, or what this shows us, is that if K is negative, the resultant vector will be in the opposite direction. So if we have if we're multiplying by a negative scalar, this will result in a resultant vector in the opposite direction. Positive K, the vectors will be in the same direction. Negative K, the vectors will be in the opposite direction. The final item to cover in this topic is calculating the magnitude of a vector. Now, as we stated earlier, a vector has both size and direction, and the size or length of a vector is also known as its magnitude. And in mathematics, we show the magnitude of vector A as shown in yellow here. It's A with the 2 bars around it, a bar to the left and a bar to the right, and this is vector magnitude notation. Okay, so the magnitude of a 2D vector can be calculated using Pythagoras theorem. Now recall from the Pythagoras section of this course, the Pythagoras theorem is applied to right-angled triangles. Here we have a right-angled triangle where A is the hypotenuse, the longest side of the triangle, which is opposite the right angle, and the other 2 sides are B and C. So Pythagoras theorem states that A squared equals B squared plus C squared. The square of the hypotenuse is equal to the sum of the squares of the other 2 sides. And we can work out A using this. A is equal to the square root of B squared plus C squared. Now, if you need more information on Pythagoras theorem, then obviously refer to the Pythagoras theorem section of this course for more details. Now, what does this mean in terms of our vector? So we can represent vector A in component form. So we say vector A has components x and y, and we know that this makes a right angle also. So vector A can be represented as the hypotenuse of a right angle triangle with sides x and sides y. So in general, we can calculate the magnitude of a 2D vector using Pythagoras theorem, and for 2D vectors for a 2D vector A in xy, components xy, the magnitude of A is equal to the square root of x squared plus y squared. So as you can see, Pythagoras theorem, A is equal to square root of B squared plus C squared. So for vector A, the magnitude of vector A is equal to the square root of x squared plus y squared. So let's have a look at an example. Let's say we have a vector A and it has components 3, 4. Then the magnitude of A is equal to the square root of x squared plus y squared. So that's 3 squared plus 4 squared. So the magnitude of A will be square root of 25. So A is equal to 5 units. So the magnitude of A is 5 units. So as we can see, we can calculate the magnitude of a 2D vector using Pythagoras theorem, and the magnitude of A is the square root of x squared plus y squared when we have vector A in component form. Okay, that concludes this topic on 2D vectors. There's quite a few key concepts to take in here in terms of opposite vectors, equal vectors, multiplying a vector by a scalar, vectors in component form, and calculating the magnitude of a vector. So as always, to bed in these concepts and to hone your skills, it's now time for you to go off and practice.